Okay, so this is 522. It is October 1st. And today we're going to recap the MANOVA procedure a little bit, see how it relates to discriminant analysis. And then in the second part of the lecture, we're going to get back into James and look at some resampling approaches. So a quick recap of what we did last time. So we looked at a procedure called the discriminant analysis, where in the discriminant analysis, we had a response variable that had two options. Okay, so it was binary, and then we had a predictor variable. And the predictor variable, we're just going to put as continuous for now. So this response variable is binary. It's got two possibilities, and that's different from ordinary least squares regression, where this would be a continuous response variable. So right away, you know that when you're dealing with binary variables or multinomial variables, you're into something that's different than ordinary linear least squares regression. And that's what we developed in the first part of last week's lecture, is that discriminant analysis procedure. And that discriminant analysis is coming from James. So you're interested in classification into groups. Now, in the second part of last week's class, we looked at how a technique called the multivariate analysis of variance is actually contained within this discriminant analysis. Okay, we said that MANOVA is actually found within this discriminant analysis. But in James, they don't talk about MANOVA. So MANOVA is completely out of the picture. They don't talk about it except for the fact that they do mention, kind of in passing, when discussing discrim, they discuss the idea of mean vectors. And we pointed out last week that it's right there where they talk about mean vectors, where they're actually hinting at the presence of MANOVA. But that's as much as they develop it. Okay? And we said last week that there's actually some reasons for that as to why they do not go into MANOVA. Based on the nature of the book, they're mostly interested in simply classification. So they want to take X1, X2, X3, however many predictors you have, and they want to predict what group you can come from. Kind of like, are you committing bank fraud or are you not? Are you committing credit card fraud? Are you overusing your credit card because you're using it several times in a row? Well, then maybe you'll be classified into the group where the hypothesis is that you are committing credit card fraud versus the group that is assumed that you're not. Okay, so that's the focus of that discrim procedure coming from the book. We had to switch books a little bit to get into Stevens, and the reason for that is because not only is the MANOVA contained in this setup, but it may be of interest for a researcher to actually conduct a MANOVA. Now, how does this arise? How does this arise? Well, let's say that we have more than one predictor in the discrim. So I'm just going to put 2 for now. Well, let's go with 3. There's 3. Okay. So we have 3 predictors here. Well, we know that we can conduct a discriminant analysis on this by putting X1, X2, and X3 in the model and make it predict the binary response. We know we can do that through discrim. But what we talked about last week, what all this stuff was down here, was what if we flip this equation around? So I'm going to flip it around, and I'm going to put X1, X2, and X3 here, and I'm going to put Y over here. Okay. So this becomes now my dependent variable on this side, and this is my independent variable on this side. Now, usually we'd call these by the name of Y, and this by the name of X. I'm just keeping this notation just so you see that where the flip is coming from. So I'm going to name this the DV column. This is always the DV column, no matter whether we call these Y's or X's. The left-hand side is always your DV, and then your right-hand side is your independent variable. So what does this function statement say? Okay, so this is the function statement. We're saying these variables, right, these variables are a function, right, are a function of the independent variable. Okay. So you can see right away that in a simple linear regression, we have something like this, where you have only x1 and you have a continuous y. There's your simple linear regression. For your multiple linear regression, you have several x's and you have a single y, but it's continuous, right? Simple linear regression, this has to be continuous. Multiple linear regression, this has to be continuous. So you see what's happening in the flip here is we want to predict a linear combination of these particular variables. We're wanting to predict a linear combination of these variables x1 through x3. Now, we often don't say it that way in the MANOVA context because this variable here in MANOVA is going to be binary or it's going to have multiple categories, but this is going to be categorical, just like we would have a factor in the analysis of variance. Okay, so we're building off the ANOVA model over here. So the question is, why would we want to do something like this? Why would you want to flip this around and do something like this? And clearly our book doesn't really see the point in doing it because their only mention is of mean vectors. They do not develop the MANOVA model, nor do they say that this would actually be a good model to run. They don't even entertain this as a possibility. So why would you want to do it? Well, we said last time that maybe you have a few variables like verbal ability, quantitative ability, and analytical ability, and you think that those variables, in some sense, should go together. Okay, they should go together. They should go together and produce what we could loosely call a composite variable. Okay, a composite variable, or if we want, we can give a different name to it. We can call it a variate. We can call it a variate. Now, what's a variate? Well, it's made up of several variables. It's a linear combination. So this whole thing is a linear combination. So I'm going to write my linear combination as V, Q, and A. And to produce the linear combination, I'm going to need weights over here. So I'm going to need a weight here, a weight here, and a weight here. These weights we generally just call by the name of scalars. So I'm going to have A times V plus A times Q plus A times big A. That's going to produce the linear combination of V plus Q plus A. And this thing here, I might identify for convenience as IQ, right? I might say, IQ is made up of a combination of V plus Q plus A, okay? This is what this left-hand side is actually representing. It's a linear combination of variables. I'm choosing the variables V, Q, and A. But technically speaking, these could be any variables. So I've got V plus Q plus A. So the question is, when you look at it from this perspective, is what values of A should I choose? Okay, what values of A should I choose for this linear combination? Well, if we were to produce this naively, and by naively, I mean without any kind of multivariate analysis technology, right? Just kind of like, let's just do this like before statistics arose, right? We're like in the 1700s and we say, hey, we want to produce a linear combination. How would you do it? Well, you might take verbal, quantitative, and analytical, and you might reason with your colleagues that, verbal should get 2 times the weight of quantitative and analytical. So in this, what I've done is I've assigned 2 times V plus 1 times Q plus 1 times A. And that's how I've chosen naively, or we're in the 1700s again, okay, that we've chosen naively to compute this linear combination. Now, it's a naive linear combination because it doesn't satisfy any function. It's not guaranteed to do anything other than just kind of satisfy our interests of how we think it should be defined. But it doesn't have any mathematical properties. It doesn't have any optimization properties associated with it. So that's why we're calling it naive. We're calling it naive because we've kind of just decided on those scalars through no mathematical means, no rational means, no technological means. Okay? Where MANOVA is different, and the ensuing discriminant analysis is different, is it chooses these scalars. Okay, it chooses these scalars in a very, very intelligent way. So it says, what should this scalar be? What should this scalar be? And what should this scalar be? Now, what do I mean by it does it in an intelligent way? It does it in such a way that it's going to optimize some function of the data, right? It's going to optimize some function of the data. Now, if we go to our linear regression, optimizing a function of the data is not new because we did the same thing when choosing values for A and B. Right? We chose values of A and B such that it minimizes the sum of squared errors around the line. These were very, very particular values that were chosen. We couldn't just choose them naively. If we chose them naively, what would we get? We would not get the least squares line. We'd get some other line. And then we'd lose our guarantee of minimizing the sum of the squared errors. So the same idea is here in terms of choosing our scalars. Now the technology is going to choose the scalars, but we have to understand, why is it choosing certain scalars? Well, look in the MANOVA context. So we're going to put a scalar here, and a scalar here. By what means might it actually select scalars? I mean, what function could it possibly be satisfying in this context? What function could it be possibly satisfying? Well, the only really way to understand that, or at least the most convenient way to understand that, is to flip the equation back to this. And what this says, if I put the scalars here, I'm not numbering them. There's 1, 2, 3. What this says here is that those scalars should be chosen, right? The A1, A2, A3 should be chosen in such a way that it satisfies some criteria when predicting the response. Well, what criteria should it satisfy? What do we want it to do? You know, what do we want this linear combination to do? What we'd like it to do is separate these groups as much as possible, right? We want to get separation of these groups as much as possible, maximum separability. So that's exactly how the discriminant function is actually choosing weights of that linear combination. It's choosing weights so it maximizes group differentiation. In other words, no other weights will do a better job at separating those groups. Okay. Now, when you think about it, that's not all that unlike linear least squares regression. Because in linear least squares regression, you know, if I go OLS regression here, my Y had a whole bunch of little categories, right? Had a whole bunch of small categories, had so many categories that we just said, you know what, let's just treat it as continuous. But you can think of it as your independent variables or your predictors as being chosen to kind of maximize all these little group differences on the response variable. That's a powerful way to think about this, to kind of draw an analogy with these two things, because the only difference really is that this is continuous and over here, it's binary or multi-category, depending on what we have. But the principle, I mean, it can't be that different. Okay, the technical details are different, but the principle can't be that different. That we're selecting a linear combination of variables to kind of help us maximize this prediction. That's what we're doing in least squares regression. So in other words, if we want to predict this one versus this one, well, this one should differentiate those categories. I put categories in quotes there, right? It should differentiate those categories. These aren't true categories, but you get the idea of what we're trying to do. That's one way of conceptualizing that linear least squares. Here it's more obvious because we actually do want to maximize that differentiation. So these scalars are going to be selected in such a way that it separates those groups as much as possible. And that's the logic. Now that's in Descrim. If we flip that to the MANOVA, well, then what are we dealing with? How could we phrase this kind of similar, the technical details when we flip things around? When we flip things around, as I just said earlier, though, the easiest way to understand it is through this. So how are we choosing this scalar, this scalar, this scalar? The easiest way to understand it is to just revert to this and say, well, if we put on this side and this on this side, we want to maximize separation on this variable. That's the definitely easiest way to understand it. But we can also understand it through mean vectors. And the mean vector here is you're going to have a mean here, a mean here, and a mean here on each one of those groups. So this particular group is going to have a mean vector. This particular group, the group coded 1, is going to have a mean vector. Mean vector and mean vector. So you can see that the MANOVA problem and the Descrim problem, they're actually doing the same thing. They're actually doing the same thing, which is trying to provide separation between the groups. Only that in the MANOVA, because of the way it's formalized, we're talking about mean vectors between the groups. That's what we're interested in characterizing between the groups, rather than simply the idea of providing that separation between the groups. Okay. I hope that's clear, because it's not easy to kind of join those two together and recognize how MANOVA and Descrim are related. But they're basically doing something extremely similar. It's just that the question is different. The question is different. In MANOVA, we ask the question, are there mean vector differences between the groups? Right? Are there mean vector differences between these groups? In Descrim, we're asking, can we get a linear combination that provides maximum separation between the groups? But you can see that the scalars that are chosen, they have to be the same, because they're basically answering a very, very similar, they have basically a similar technical base. The research question is phrased in a different way, but what they're actually getting at is the same thing. Okay. Now let's simplify this for a second. Let's just simplify this. Let's take away these two variables. Right? Let's take away the two variables, and let's just go x and y. And let's go 0, 1. Well, in this particular case, right, we have a t-test. Continuous x, binary y. What question do we ask in the t-test? We ask, are there mean differences between groups? Right? Are there mean differences between groups? Well, that's all familiar, right? That's no problem. I mean, nobody's thinking mean differences between groups. Well, we've heard that before. We've heard that many times before. So that's really clear. So watch what we can do to better understand all this stuff. Flip this around, right? If we can flip it around here with the more complex model, we should be able to flip this around with the simpler model and just see what happens. So why don't we do this? Move y over here, y 0, 1, and move x over here. Well, what do you have? You have the discriminant analysis, right? You have the discriminant analysis coming from the t-test. And what's the discriminant analysis? Use X to predict group membership, right? Use X to predict group membership. Now, if you look at that, we have to choose scalars. Well, here, this is very simple linear combination. This is an extremely simple linear combination, but it can be shown that these two ideas are related to one another as well. So the only difference between this simpler idea and this one is what? What's the only difference? The only difference is that our linear combination is much simpler. It's extremely simple. We wouldn't even call it a linear combination because it's made up of one variable. I mean, it'd be foolish to call it and say, I've got a linear combination. What's your linear combination? Just X. We usually wouldn't say that because usually when we talk about linear combinations, we're talking about a combination, right? It makes sense that we're talking about X1, X2, X3, X4, what have you. But if you shrink the problem down conceptually, you'll see that this here can be considered kind of like a primitive conceptual linear combination made up of a single variable. Okay. So you see that in this situation here, you reverse it and you get the discriminant analysis again. So take it from ANOVA and t-tests, and you can play around with those things and you'll see that you're basically doing the same thing. Okay. So let's talk about the K-group MANOVA. We've talked about the two-group MANOVA, and what was the two-group MANOVA? The two-group MANOVA was Hotelling's t-squared. So the analogous version of the univariate t in multivariate terminology is called Hotelling's t-squared. Now, you're not going to find too many programs on Hotelling's t-squared. You just do the MANOVA if you have to do a MANOVA. And why is that? Well, for the same reason that you can do an ANOVA to account for a t-test. And many times programs will just not offer the Hotelling's t-squared option because they'll just tell you, just go do a MANOVA. It's the same thing because it's on two groups. So that comparison happens as well. But here we want to consider the situation of K-group MANOVA. So we've got our, oops, I'm going to just put the Y's here now. There's that, and then we have our X, and we have 0, 1, 2. All right, we have K groups, 0, 1, 2. There's 3 groups here, and we have, say, 3 dependent variables, or maybe 2, or what have you. So remember, the big idea in the Hotelling's t-squared was that we are accounting for covariance among our dependent variables. Okay, and we had to satisfy some assumptions. So, depending on whether you have 1, 2, 3, we had to look at that covariability between the responses. So we had to look at that by group, right? We had to say, well, there's equal covariance for group 1, 2, and 3. So something similar is going to happen here. Well, we only had 2 before, but something similar is going to happen here because we have more than 2 groups. We're going to have to look at that covariability among variables between groups. So this is the setup here in a dummy regression format, where this would actually be a multivariate multiple regression. And you can find that in Stevens. Okay, so this is multivariate multiple regression. We have 2 responses. Okay, 2 responses make it multivariate. Okay, that's kind of like the historical custom, is that when somebody asks you, do you have a multivariate model? Well, usually that's referring to whether you have more than a single response. Now, if you look beyond terminology for that, you realize, wow, that's kind of like superficial. And it is, because look, if I have a single y, x1, x2, and x3, that's a multiple regression. But my goodness, it's multivariate as well, isn't it? I have a single response, sure, but if I flip these around, all of a sudden I have a multivariate model. So why would I have a univariate model here, but not a multivariate model if I flip it around? It seems kind of silly to designate, one side or one technique as univariate or bivariate and another technique as multivariate, because we know by this flip, we're basically doing the same thing. So when you think about multivariate models, recognize that the underground is very, very similar, regardless of what we call it. So here we're calling it multivariate because we have the two responses, and that is usually the custom. But again, you should appreciate that that's just kind of a way of differentiating it from different procedures. We have two predictors. We have X1 and we have X2, and this is corresponding to a grouping structure. So in here we have dummy coding. So we have X1 and X2, and we actually have three groups over here. Two predictors, we've coded it as two predictors, but we actually have a three group structure here. Group 1 is represented by this, group 2 by this, and group 3 by this. So let's take a look at how we would analyze this through the multivariate analysis of variance. But what Stevens is talking about here is that if you run this as a regression, you're going to get the same effects as if you ran it as a multivariate analysis of variance. Okay, that's the point of looking at this, is that we realize that regression and ANOVA are very similar techniques. We know that from before. Well, it stands that multivariate multiple regression, right, as this setup is indicating, should be very similar to the multivariate analysis of variance, and it is. So again, deserted island, if you're going on a deserted island, which program do you take? You take the regression program, because you can do the necessary coding and figure it out. Multivariate analysis program, not so easy, because the multivariate analysis program, what's the difference between the multivariate analysis program and the regression program? Multivariate analysis is specifically designed for the grouping structure, right? That's the basic difference. So as we progress with our statistical models, you're starting to see that, wow, there's like so much going on that's the same, just kind of little tweaks and special cases of a bigger model. And that's exactly what we're seeing here. So we've got a whole bunch of regression going on here still, but you can develop a program or an algorithm, to use kind of like the modern word for it, and you can say, well, let's set up a multivariate analysis of variance to account for the grouping structure, even though we could do it if we wanted to through regression. Okay, so moving on, we have the K-group MANOVA. There's our null hypothesis. We have K population means are equal. In the univariate case, that's univariate, right? Those are just population means. MANOVA, we're dealing with vectors, right? Vectors, equal vectors. So if you're looking over here, well, we have our, or here, let's just go here, get a vector of means, equality between the groups. Vector of means, equality between the groups. There's your reference to James. So when James slips in there, hey, this discriminant analysis mean vectors, this is the exact idea they're referring to. That's not developed. So for the univariate analysis of variance, remember we used F. No problem. For the multivariate, we're going to use Wilks, and we talked about Wilks last time. And we got to see how we compute this, because it's a little bit more complicated than the Hotelling's t-squared, but we're going to compare the determinant of within to the determinant of the total. And the identities are the same as in univariate. Univariate, sums of squares total equals between plus within. Multivariate, total equals between plus within. Only that, what's the fundamental difference, right? If you were to explain somebody, if somebody, came to you off the street and says, univariate analysis of variance and multivariate, what's the difference? And I only got like 15 seconds for you to tell me the difference because I have to be on my way. What you would tell them is you would say, sums of squares is partitioned into SSB and SSW in univariate, but in the MANOVA, we have what's called the sums of squares and cross products matrices that are partitioned into between and within. And the sums of squares of cross products matrices is what we looked at last time with Hotelling's t-squared. So you've got the total SSCP matrix divided, or partitioned rather, into between plus within. And then, you leave the person on the street, they say, okay, that's good, just give me the last thing because I really got to go. What's the difference? Cross products, right? The cross products. There's no cross products in here. There's cross products here. And, and then the person says cross products. I have no idea what you're talking about. How could you also kind of communicate that? You can say that in the multivariate case, we're dealing with covariance, right? We're dealing with covariance, which is the kind of like the precursor to covariance is the cross product. So remember that in our Pearson R, right? In our Pearson R, when we do things like this in the numerator, right? In the numerator, what are we getting? We're getting the sum of cross products. Yeah, we have to divide to get our covariance and all that, but we're dealing with cross products. So you can express this idea in terms of saying, well, hey, it's accounting for the covariance among the responses, or you can just say, well, it's accounting for cross products. Both are getting at the same idea here. Okay. So there's your partition. And let's look at an example of how you compute this, because this is actually really powerful. Again, I mentioned last time that looking at the numerical computations for these things, for the MANOVA, is really, really kind of necessary just to see an example of what exactly is going on. That's not all true for all things where you actually don't have to actually look at the individual numbers, but here it's really, really useful. So there's my data. I have a three-group structure. Oops. I have a three-group structure. I have group 1, I have group 2, and I have group 3. How many response variables do I have? I have 2. I have 1, 2, 1, 2, 1, 2. So if I were to draw my function statement, I have y1, y2, and I have groups 1, 2, and 3. Multivariate analysis of variance, because I'm looking at mean vector differences. There's going to be my vector, mean vector across groups. So this is the mean vector of y1 and y2, a function of the grouping structure. Notice if you take away y2, what do you get? You get an ANOVA. If you take away y1, what do you get? You get an ANOVA. But it's not going to be the case that y1 as a function of groups and y2 as a function of groups separately will necessarily equate to the multivariate effect. So I think we mentioned this last time that you can get multivariate statistical significance, so considering these two together, but not univariate. And likewise, you can get univariate, but not multivariate. So you don't want to think of these, it would be wrong to think of these as just like two univariate analyses glued together. That would be like a horrible way of understanding this, because that would mean that you're not appreciating that you're actually producing a linear combination here, right? You don't want to say, well, y1 is equal to a group structure, and y2 is equal to the group structure, and let's just add these two things. That's really what we're doing in MANOVA, because that wouldn't be accurate. MANOVA is selecting those scalars for y1 and y2, and it's called Rao's paradox, that you can get univariate but not multivariate effects, and vice versa. So we have to consider this again, as we always talk about, we have to consider these as you're testing the model. This is the model you're testing. You're not testing individual models in here. You're testing the multivariate model. If you want to test the univariate models after, and a lot of computer software will spit them out for you, then that's fine, but it's not the same model. It's not the same model as this. This is a different model. Okay. So let's compute our within and our between. So remember, when you're thinking about the within matrix, the analogy is like SS within in ANOVA. What are you thinking of? Well, you're thinking of stuff that does not incorporate, right? It doesn't incorporate the multivariate idea yet, right? It doesn't incorporate the multivariate idea because you're not going to be crossing anything. So let's just look at the computation. 2 minus 3, 2 minus 3 plus 3 minus 3, etc., plus 5 minus 3 plus 2 minus 3. So that's within group 1. Within group 2, 3 minus, within Y2 rather, 3 minus 4, 4 minus 4, etc. And then we have the crossing of Y1 and Y2 within group 1. Now, I just want to clarify something I said earlier. I said you're not crossing anything. Now, that wasn't the best way to say that, because you're crossing Y1 and Y2 here. 2 minus 3, 3 minus 4, right? 2 minus 3 and 3 minus 4. What I meant to say is that you're not accounting for group differences. You are accounting for the Y1 and Y2, but you're not accounting for the group differences. So you've got the Y1 and Y2 being crossed here in the cross product, but what the W matrices are not doing are giving you that, that group differentiation. Okay, so please clarify that when I said the crossing, because I was kind of referring to the group structure, but that could easily be taken as the crossing of the dependent variables. There's a poor word choice for that. So I've got the X1 or the Y1 and Y2 working its way here, but nowhere in the W term is there any mention of the group differences. There's no mention of the group differences. So I get my Y1 happening right here. And then I get my Y2. So I compute Y2 as well, and I compute Y3 using the same ideas as we have here. And then I pool them together. Okay. I pool them together, W1, W2, W3. Again, what makes that the W matrix? Makes it within, because I'm not looking at the group structure. I'm just pooling the within. Okay, I'm pooling the within. You can liken that to the analysis of variance, where in analysis of variance, I get the pool term, right? So I get a variance here, I get a variance here, I get a variance here, and I'm pooling them together using the pooled variance term. What is that pooled variance not doing? It's not reflecting group separation. It's just reflecting kind of what you would expect to see if there is nothing going on in your theory, in your group theory. Because this you can think of as being a theory, group 1 versus group 2 versus group 3. And the W is just looking at that within over here. Now, the idea behind the between is it's now going to incorporate those between group differences. Okay, the between group differences. So how's it going to do this? Well, you look at Y1, what it's doing here is you have the 4, right? The 4 is the number. Okay, so that's just the number. That's just a multiplier. Again, that 4 is not, that multiplier is not the exciting part, because that just depends on how many observations you have in the particular under Y1 over here. Then you're taking 3, which is the mean right here, minus 5.67. Now, what is the 5.67? Well, the 5.67 is the mean of y1 across the groups. Okay, it's the mean of y1 across the groups. Now, how are you going to get that mean? Well, unfortunately, you cannot go 3 plus 5 plus 8.2 divided by 3 because you have unequal n per group. So the way this 5.67 is computed is going 2 plus 3 plus 5 plus 2 plus 4 plus 5 plus 6 plus 7, 8, 10, 9, 7 divided by that total number. Divided by that total number of data points that went into that sum. And that's how we're getting the 5.67. So you see what the term is doing. You can do the same thing for the second y2, and you're going to compute that overall mean for that variable in the same way. It's going to be different than this one just because it happens to be different for the data, but it's computed analogously as to how we computed this one over here. Okay, then what you're going to do is you're going to cross the terms. You're going to cross the terms. So when you look at this, we're taking the 3 minus 5.7 times the 4 minus 5.75. 3 minus 5.67 times 4 minus 5.75. This is where the crossing is happening. This is where the crossing is happening. But you know, what I was alluding to earlier, when I said, well, there's no crossing here, but there's crossing here. Well, there is crossing here because you have the y1 and the y2 crossing. They're crossing here. You're getting the cross product. But this is where the actual hypothesis is, right? This is the hypothesis. This is the reason why you're doing the MANOVA, right? You're doing the MANOVA because you want to see whether there's a crossing here, not only within groups. This is not interesting. I mean, the fact that these cross is not really interesting. This is what's interesting, right? This is what's interesting because this is the crossing across groups. The hypothesis, another way of putting it, is all in this. This is why you're doing the MANOVA right here. Okay? This is why you're doing it. So 3 minus 5.67 crossing by 4 minus 5.75 plus accordingly for the others. And this is measuring that idea of between, right? Of the between separation. Whereas this one is only the within. So when I compute my B matrix, so I compute these terms and then I add them in. So there's between for group 1, between for, y1, y2, and then this is for the grouping structure. And I'm going to put those in the in this matrix B. Okay. So the reason here, I just want to kind of highlight this point because it's actually, you know, really, really important. If you look at that y1 again, you know, y1 is 3 minus 5.67 plus, then we said 5 minus 5.67 plus 8.2 minus 5.67, 3 minus 5.67, 5 minus 5.67, 8.2 minus 5.67. Notice that when we took that computation, we're only under y1, right? We're only under y1. We're going across the groups, but what are we actually doing, right? That's not the multivariate part. This is just y1. We're only doing this for y1. So here, you're kind of still in univariate land, right? It's like you're doing a little univariate analysis when you're computing this term. This is kind of what you're thinking when you're computing this term, saying, wow, we're still kind of in, that's kind of what we would do in univariate if we were just looking at y1. Because I'm only going under y1. There it is for y1. There it is for y1. There it is for y1. You see, that sounds a lot like univariate. And it is, because that's what you would do for computing in univariate. Same thing for this one. Only we're doing it under what? y2. y2, y2, y2. That's why I say here, this is the hypothesis. This is where the big stuff happens, because otherwise you're still in univariate here. When you start doing this stuff, you're into the multivariate. Okay. So I hope that point is clear, is that in both of these is where you are into that multivariate idea of the MANOVA. But this one here is definitely, this one, if you compare this term to this term, this one's the most important up here. This one, all of this stuff is most important because it's in here where it's kind of like the analogous to the, the main hypothesis that you have compared to over here, which is, this is just kind of pooling all that within stuff. It's taking into consideration the covariability, those cross products, but this here does not care about group structure. Okay. This one here does. So this is the primary idea for the multivariate. So when we put these through, we have T is equal to B plus W. So we said that we can partition these matrices into between and W over here, and that's what we get. Now, sometimes these matrices here, because I said this is kind of like the hypothesis, well, there's a lot of books that actually say total is equal to, just call it what it is, the hypothesis matrix, plus what's the W? Well, what's W really accounting for? Kind of accounting for that kind of deviation, cross deviation that's not due to group structure, right? It's kind of like, this is the necessary term we have to, this is like the denominator, right? We just have to compute that denominator where all the good stuff is happening up here. So you can call that the error matrix. So the total is equal to the hypothesis plus the error matrix. And that's probably a better way of actually writing those things than saying it's between and the within, because that really tells you what that between is actually doing. Okay. So we can calculate the Wilks lambda just as we did for the special case of the Hotelling's T. We compute our Wilks, we evaluate it for statistical significance, and there's our value right there. It is statistically significant, so we can reject the null hypothesis. And what's the null that we're rejecting? We're rejecting mean vector equality on those two variables. So when we reject that, we say we have evidence that there are group differences on the linear combination of y1 and y2, or equivalently, we can say there's mean vector differences between the groups. What's the vector? y1 and y2. Okay, so that's what that's telling us. Now, there's other multivariate tests here. We're not going to get into these. Stevens doesn't get into them, and this we can kind of break down. This could be like a 30, 40-minute discussion as to what all these different tests do. So right here, I'm just going to get a very, very tell you what to do is, if you look at Palais trace, Wilks lambda, Hotelling's trace, and Roy's largest root, these will usually suggest the same response on the null hypothesis. Okay, they usually will, because you can define these things in terms of eigenvalues and all kinds of things, but they'll usually hint at the same decision on the null. If they don't, well, then you have to look at your data a little bit more closely to find out why they're suggesting different answers. Okay, for instance, possible that it happens that one test rejects, but another test doesn't. Well, you got to get curious about that. And you have to look at your covariance matrices to try to see how your covariances are set up. It could mean that you have one eigenvalue that's dominating versus others that are not, that you have actually one primary discriminant function in your analysis, whereas the other discriminant functions are not very important. But I can say that usually when you're conducting MANOVA, you're going to have all these reject. And if not, then like I say, like dig into Stevens, go there and read a little bit more of that discussion. And you may actually have to dig further and look at those covariance matrices, see what's going on. So that ends our discussion of MANOVA. In Stevens is a lot more detail, discusses power, discusses follow-up analyses like Tukey post hocs on these types of things that you can look at if ever you have to do a multivariate analysis of variance. But our point here is to kind of describe a little bit of what's actually happening in the MANOVA, but also to relate it back to the James stuff, that the MANOVA and the discrim problem are actually very, very similar. They're just phrased in different ways. Okay. One more thing is, and you'll see this on the next assignment, is if I draw my discrim here, James doesn't talk about this in discrim either, where you have 0, 1, and you have x1, x2, and x3. It may happen that you may be interested in the nature of this function. Okay, what do you mean by the nature of the function? Well, you may want to know more about those scalars that are weighting the function, a1, a2, and a3. So in the book, they don't talk about this. They just talk about predictors or linear combination maximizing separation between the groups. But they don't care to know about the nature of this function. Well, in the spirit of multivariate analysis, sometimes we want to know the nature of that function. In other words, could we give this a name? Right? Can we give this linear combination a name that does so good in maximizing separation? And if I told you that that linear combination, to use our previous example, was made up of verbal and quantitative and analytical, and I told you that the optimal function that it's using to provide this discrimination was like 10 times verbal and only 1 time quantitative and 1 time analytical, we may be interested in looking at this and saying, you know what, this, I'm putting in quotes, dimension, it's not specifically a dimension in the form of principal components analysis, which we'll talk about. But if I kind of call this like a variate or a construct, and again, I use those words carefully because usually when we talk about dimension, I don't want to confuse that with principal components analysis or factor analysis. So don't think that when I say, well, here we have a dimension here that's equivalent to principal components. You can consider it to be a dimension, just don't equate it with principal components analysis that we talk about later, because they're going to be a little bit different. But if I wanted to, I might say, well, this is 10 times verbal, 1 time quantitative, and 1 time analytical. Maybe this thing, this variate, is mostly made up of verbal. So whatever is doing the discriminating is mostly a verbal thing, but also contains a little bit of other things, kind of like a mixture, right? Almost the idea of who's going to survive from COVID versus not. Well, maybe this is age, this is prehistory, you know, pre-existing conditions, and this is, you know, do you wear a mask? Well, maybe the dominant thing is pre-existing conditions, so maybe this would receive a bigger weight than the other two. Again, the book is not going into detail as to understanding the linear combination, because they're mostly interested in just predicting the classification. But as you'll see in the assignment as well, sometimes you actually want to learn more about it, and sometimes these functions are worth unpacking into why they're weighted the way they are. Okay. In other words, what's the nature of the linear combination that's actually providing the separation, right? Once you determine that there's a linear combination, one or more linear combinations that are providing separation, you may want to actually learn more about it. And that's what that's about. And you'll get a question like that on the assignment where you have to unpack that linear combination a little bit. Okay, so that's it for multivariate analysis of variance. Let's take a quick break. We'll come back and we will do part 2, and we'll talk about resampling techniques back in James. So we'll be right back.